So on the worksheet, we have this chart right here, which shows Austin, Portland, and Bismarck. And basically, the first mark represents the P wave that hits each of these cities. So each of these cities know that there was an earthquake that occurred somewhere because a P wave hit them. And then sometime later, the S wave hits them. Now, this difference in time is caused by the fact that P waves move faster than S waves. So as the P wave moves through the Earth and gets to each one of these cities, the S wave is coming behind it. Now, the further away the city is from the epicenter, the further amount of time, the more time, which we call lag time, between the P wave and the S wave. So based solely on this, you can see that Portland is going to be closest to the epicenter because the P wave and the S wave are closer together than the other two cities. Bismarck's going to be the furthest away because the lag time is much greater for those. So in looking at the lag time for each one of these, we see that Austin has a lag time of 300 seconds. Now, in our packet, we have a graph that says that 300 seconds gives us a distance to the epicenter of 1,875 kilometers. For Portland, the lag time is 240 seconds, which the chart gives us 1,500 kilometers. And then for Bismarck, it's 340 seconds, which the chart gives us 2,125 kilometers between Bismarck and wherever that epicenter is. So starting with Austin, we know that Austin has a distance of 1,875 kilometers. Now, we don't know what direction the epicenter comes from, so if we draw a circle that is 1,875 kilometers away, then we know that the epicenter is somewhere along this circle. We just know how far away the epicenter is. We have no idea what direction it is. So the epicenter could be along any point on this entire circle, which basically means an infinite number of locations that we could have the epicenter. The epicenter could have come from the north, it could have come from the east, come from the west, come from the south. Who knows, because we only have the amount of distance away that it is. So then we go to Portland, and Portland says that, well, the epicenter is 1,500 kilometers away from us. Well, we draw a circle for Portland all the way around, and we see that Portland's circle intersects with Austin's circle at two locations. So that means that Pierre could be an epicenter, as well as San Diego, because those 2 points are both 1,875 kilometers away from Austin, as well as 1,500 kilometers away from Portland. So in order to really refine this, in order to get down to one location, we need a third point. In Bismarck, what it does is we get the distance for Bismarck, which we found to be 2,125 kilometers, and then we draw our circle around there, and we can see that that will intersect at a very specific location. So the spot near Pierre is not the epicenter is near San Diego. And that's because the distance of the epicenter from each one lines up right there. Now, this process is referred to as triangulating, because what it does is it basically takes three different locations, and then you figure out where that epicenter is based on those three different locations, and then since we know how far it is away from each one, then it can be only one possible location, and that is San Diego. So this diagram, we see the direction that the plates are moving as well as how fast they're moving. You can see that the North American plate and the African plate are actually moving away from each other kind of slow. The purple represents a very slow movement. But then the Pacific plate is being essentially being destroyed, so it's being pushed a lot more. So the North American plate and the Australian Indian plate, that is pushing on the Pacific plate, basically making it move pretty fast and destroying it in the process.
From the creation of ice ages to the effects of global warming, the Earth's climate is a roller coaster of change. And our next great discovery helped put it all into perspective.
For centuries, people believed that the Earth was shaped by catastrophes, like the biblical flood. But in the early 1800s, an Oxford-educated lawyer named Charles Lyell shattered that belief and revolutionized geology.
Lyell spent years traveling the world, studying an overwhelming number of rock formations and fossil samples. He had a brilliant eye for detail, and piece by piece, he began to see that the rocks told a different story. While catastrophes such as volcanoes, earthquakes, and floods occasionally affected the planet, The greatest changes were the result of an incredibly slow and natural geological process, a process driven by wind, water, erosion, and the heating and cooling of the Earth. A record of those changes was contained in the layers of rock. But here was Lyell's most radical insight. The mechanism for that slow process of geological change was time, lots of time. The Earth, Lyell argued, was far older than was generally accepted, and he presented proof of his findings in a landmark book called Principles of Geology. Today, its publication is considered the birth of modern geology. Sam Bowering is a professor of geology at MIT.
I think very important in Lyell's development of thought was a trip to see the volcanoes of Italy and Vesuvius, I believe in particular, where he actually saw that the mountain was built up of successive flows, and they had some of these had a good idea of when they were erupted because they were historic, and he was able to use that to extrapolate that the volcano itself must be hundreds of thousands of years old, and at the time talking about hundreds of thousands of years was revolutionary. Others argued for a directionality in evolution, that the Earth on day one is not the same as the Earth today. Some secular change has occurred, and this is a debate that geologists have today. Were plate tectonics operating 4.5 billion years ago, or is it something that developed later on in Earth history?
Today, many consider Charles Lyell to be the Charles Darwin of geology. In real life, the connection between the two men was significant.
Darwin took a first edition copy of Volume 1 of Lyell's treatise on his cruise with the Beagle. And what he realized from reading this, as he was also simultaneously worrying about evolution, was that here was the solution to evolution. We had limitless time.
Lyell's discovery set off a firestorm of interest in determining the true age of the Earth. Until then, most everyone believed that the planet was young. But with the publication of Lyell's seminal book, geologists wanted to know how young. Our next great discovery provided an answer.
So there are two ways in order to determine the actual age of rock layers, and the first one's going to be relative dating. The first assumption that has to go along with this form of dating is that there are no changes in the rock layers, and as long as that's true, that means that the youngest layers are going to be at the top, and the oldest layers are going to be at the bottom. So in this diagram here, you see that A is going to be the oldest layer, B is going to be a little bit younger, then C, and then D is going to be the youngest of all of them. This is referred to as the principle of superpositioning. So if you were to look at this example and then say which layer is going to be older, whether it's going to be D or B, then you would say that B would be older. And that's fairly easy, because if you think about it, then if you kind of think of a stack of papers, the bottom layer, the bottom paper is going to be the oldest that's going to be turned in, and then the one at the top is going to be the youngest, going to be the one that turned in the most recent. So the Grand Canyon is a great example of relative dating. You can see the rock layers here as you move up in the Grand Canyon to the top. You can see that the rock layers are definitely different, especially off here. You can see that those rock layers are very definitive. And the reason you can see these rock layers is because the Colorado River has cut through this area over millions and millions of years to be able to cut away at this area, and you can see those right there. This picture just kind of shows the different formations that are inside of these rock layers. What actual material rocks there are in those layers. Let's take this example where you got all these layers of rock that have formed over millions of years. Now, in order to determine which one is older or which one is newer, then if you have to look at some of the processes behind what creates a rock layer. So if you look at this, you can actually see that B was created before K, because K is basically where magma has come up after B and A have been created and kind of formed itself there. But if you look at C, C is where it stops, which means that K came up and formed, but then C overlaid on top of it. D is going to be after that, so B is going to be first, then K, and then D. So B is the oldest, D is the newest, and then you can see this area here where there's a slippage between these two layers of rock, and the reason these are slanted is because they used to be horizontal, but there was some uplifting according to maybe a convergent boundary of sorts where it pushes all of that up. And then after D, the next youngest is going to be J, and then we have L. So if you look at all the layers here, B is going to be the oldest, and then K, and then D, and then J, and then L had to come through after J was already formed. So that's going to be the order by which the rock layers are from oldest to youngest. The next type of dating is called absolute dating. So radioactive materials are found in rocks, and these radioactive materials have a specific amount of time at which they decay, or which they transfer from radioactive to more stable materials. The process of determining the age is referred to as radiometric dating. You may have heard of carbon-14. Carbon-14 has a specific half-life, so the half-life of the radioactive material will decay into a more stable material, and that amount of time is almost constant given many circumstances. So if you think of carbon's actually caused by the sun. Its rays coming into the atmosphere, turning nitrogen into carbon, and then that carbon reacts with carbon dioxide, and then plants will absorb that carbon dioxide through the process of photosynthesis, and then animals and people, that we eat plants, and then that carbon-14, that radioactive material, will actually come into our bodies. Now, it doesn't harm us, but what it does is when we have we eat that radioactive material, it comes in, and then it goes out, so we get a constant flow in and out of this carbon dioxide. And in that process, we basically have a steady amount until we die. And when we die, we have a set amount of carbon dioxide, and then it tailors off or trails off from there. Now, how do we know how much carbon-14 did we start with? Well, that's based on how much stable material is left behind as well. And I have an example to show this, but taking the proportion between what is radioactive and what is stable, you can determine how many half-lives, and in essence determine how long since that object has died. So let's say that we have 16 grams of this radioactive material, and each of these dots represents 1 gram, and we'll call radioactive material Rm2. After 2 years, we'll consider that our half-life. Half of the material will transfer over, will become more stable. Now that material is still there, it doesn't disappear, but we have 8 grams that have become stable material. The other 8 grams are still radioactive. Now, continuing in this process, after another 2 years, then another half. So we got 8 grams left over. After 2 years, another half becomes stable. So if you notice, after 2 half-lives, we now have 4 grams, and we have 12 grams of stable material. Continuing on, after that 4 years, if we have another 2 years, that means another half is going to become stable. So we get half of the radioactive material 2 becoming stable material 1. All right, so after all this time, basically what we can see is we have 2 grams of the radioactive material, and then we have 14 grams of the stable material. And basically we can run a proportion in order to figure out, based on how much stable material we have and how much radioactive material, to determine how many half-lives there are. So we can compare this radioactive material left with how much material total and find how many half-lives. And in this process, we have 2 grams left over of radioactive material, and then we have a total of 16 of radioactive and stable. So if we run a proportion, we get 1/8, which is 1/2 times 1/2 times 1/2. That's 3 half-lives, and each half-life is 2 years, so we know that this is going to be 6 years. Similarly, with carbon-14, we can figure out how much nitrogen, which is actually what it decays into, how much nitrogen is left over and how much carbon-14 is left over, and based on those two, we can figure out how many half-lives, and in essence how long ago the object died. So we look at this scale right here, and basically this shows what happens with as a radioactive decay. So let's say we start with 100 grams. 100% of the atoms are all radioactive. After 1 half-life, which in our example was 2 years, then 50% is now going to be radioactive. So half of them have decayed into something more stable. And then after another half-life, which for us was another 2 years, then another half. So the 50% is now down to 25%. And then another half-life after another 2 years is going to go down to 12.5%. And then another half-life is going to be 6.25%. So it keeps diminishing by half every half-life that it has. Some examples of some radioactive materials other than carbon, because carbon's only about accurate for about 10 half-lives, but uranium is very accurate for billions of years, and that's actually what we use in order to determine the age of our Earth. Now, you'll notice uranium doesn't go straight to lead. There's a lot of steps in between in order for uranium to go to lead, and that's why it takes so long in order for it to have its half-life, because there are so many materials in between. You also have uranium-235, which has a little bit shorter half-life, and then thorium. These materials right here are what's in the center of the Earth, in the core, in order to add heat to the Earth as time continues on.
Exactly how old was the Earth? The question persisted until 1907, when American chemist Bertram Boltwood discovered a way to make the rocks and minerals of the Earth provide an answer. Scientists already knew that rocks contained naturally occurring radioactive elements, such as uranium. They also knew that each element decayed into other elements according to its own rate or clock, and that rate almost never changed. While studying these rates of decay, Boltwood found that mineral samples of uranium always contained traces of lead. It was an indication he believed that lead was the last element remaining from uranium's slow process of decay. From this observation, Boltwood put it all together. If he measured the amount of lead contained in a uranium sample and calculated it by the known rate at which uranium decays, he could determine the approximate age of the rock. It was a breakthrough discovery. Suddenly, scientists had an extraordinary and accurate new tool for calibrating the geological history of the Earth. It was called radiometric dating.
The great thing about radiometric dating is that it allows us to determine the age of the rocks in the Grand Canyon with quite a bit of precision, so that we can understand the whole history of deposition of these rocks before the canyon was carved. We know that the rocks in the very deep part of the canyon are 1.7 to 1.8 billion years old, and yet they're overlain by a flat surface of sandstone that's only 530 million years. So without geochronology, we would never know that we're missing more than 1 billion years of history across that surface. Now, other places in the world have that history. Here we don't have that history, and that's the important thing to remember. The geologic record is remarkably incomplete.
So a century ago, geochronology, time in the Earth, a century ago, what was it, an accuracy of 10%, 50%?
100 years ago, we didn't even know what we were dating, so uncertainties were much, much larger. They were getting dates of around 2 billion, which, of course, was a huge breakthrough in terms of understanding how old the Earth was, but it was only half of the true age of the Earth. And it really wasn't until the 1950s that people began to date meteorites that we began to realize that the Earth was probably 4.56 billion years.
To appreciate how much time that is, consider this. If we compare the entire history of the Earth to a span of 24 hours, 1 million years would go by in about 30 minutes, which means that the entire epic story of human civilization would be over in less than 1 second. Not even a tick of the clock. So why is this so important?
When we look at the history of evolution is punctuated by incredible extinction events. The Permo-Triassic extinction 251 million years ago killed 90% of everything that lived in the oceans. So the question is, was this sort of a gradual process where we saw increasing amounts of extinction, and then finally the last hurrah? Or was it catastrophic? Was life wonderful on the Permian Earth, and then suddenly everything went extinct? The way to answer that question is through high-precision geochronology. And the data that's accumulating right now suggests that it was an extremely rapid event. So as soon as you say a rapid event, the one model we have that works very well is impact of an asteroid. And recently there has been some evidence put forth that suggests there may have been an asteroid at that boundary impacting the Earth. The other aspect of extinctions that's really important, and to some people even more exciting than understanding the extinction itself, is What happens to the ecosystems? How long do they take to recover? When you wipe everything out, it's like resetting the whole evolutionary clock, and then you allow new things to fill the ecosystems that were completely obliterated. It could be that if it weren't for that extinction, we wouldn't have seen the rise of dinosaurs and then mammals. We could live on a very different planet. We wouldn't live here.
You look at this view and you feel like an insignificant speck.
Right.
And the grandeur of it is astonishing. But then when you think about what you can learn from it, then it's a whole nother level of...
It is. And it's like a book. There's lots of information there waiting for us to extract it, information that we haven't even thought about asking the rock record to produce for us. So there's a lot to do.
Well, that's job security for science.
Yes.
The Earth is a complex and dynamic planet. The crust is shifting, the mantle is moving, the atmosphere is constantly in flux. All the species that live on the Earth are changing along with it. Our ancestors did, or we wouldn't be here. The Earth challenges all living things, and so far, life has been up to the challenge.